My defense topic is the distributed acoustic sensing and for the seismic time strain inversion for subsurface monitoring. So this is to fulfill requirement for PhD in electronics and telecommunications. So my supervisor, Martin Landro, and co-supervised by Berke Onsen. Outline of my talk about my thesis today start with introduction. I will introduce you about the seabed seismic and 4D seismic methods for subsurface monitoring, and then we'll describe the objectives of the thesis and the structure of the thesis. Then I will discuss some results about fiber-optic distributed acoustic sensing, or DAS, and second half is for 4D seismic time strain inversion, and end with the conclusion. First, start with the seismic methods for subsurface monitoring. In the morning, I gave a lecture about this, but now I repeat it. For subsurface monitoring, we try to use the seismic source at the surface and propagate the wave downward to the earth, and at some strong velocity contrast, there will be some reflection of the wave return to the seismic receivers we point on the surface. And on the right-hand side show what you can get on the computer, where the vertical axis is time, recording time, and on the horizontal axis is receiver channel. So this is kind of seismic profile. And if you shoot the seismic at every shot, and you have several shot profiles, and then you can process it and build a subsurface seismic image, like in this figure. So, and then you can imagine a lot of applications about the exploration and use for like subsurface resources, something like that. First, I focus more on in the marine environment. So normally we use seismic streamer deploy behind the vessel as the receiver, and then we have air gun as a source. This is a traditional way to acquire seismic data for marine environment. And there's some limitation on this because only receiver deploy behind the vessel. That means you only record narrow azimuth of the seismic reflection data. And only P wave or pressure waves are recorded because the streamer is in the water column. And the image is typical like this. And you will have some problem about the shallow gas effect, something like that. So people try to move to ocean bottom seismic sensors. Here we deploy the seismic receiver on the seabed, and it's the geometry of the receivers are independent of the source. So now it's have opportunity to acquire wide or full azimuth of the seismic reflection data. And then they record both P and S wave, P for pressure and shear wave for S wave are recorded. And then you can get better seismic image below gas body, something like that. So recording system in the seabed seismic exploration, normally the first one is about ocean bottom nodes, or OBN. So this technique is receiver is a node. There is no cable attached to each seismic receiver. So it's a blind recording system, and it's sparse sensing points because you need to limit your geometry. And each node powered by internal batteries constraining the operation time duration. So you need to have good management, how to deploy, how to pick up and load the data to the computer. Another system that people normally use is ocean bottom cable, or OBC. This can be a real-time monitoring because it have some cable connect to each seismic receiver and connected to the recorder. So you have option for real-time monitoring, and it has dense sensing points along the cable. But the drawback is that electronic and power components are required at the sensing points. Another option is to use fiber optic. So fiber optic distributed sensors. This option maintain the real-time monitoring option and dense inline sensing points, the same as OBC cables. But because the receiver itself is based, the mechanism itself is recorded by the optical system, so no bulky components at each sensing point. So, and this is it. We focus on the application of the fiber optic distributed sensors for these advantages. So the first thing is about the issue of spatial sampling. That normally, if we have a node or the sparse receiver geometry, for example, receiver interval quite sparse, 50 meters, your seismic record will be like this, and you can see that there is a spatial aliasing problem, especially for ground roll, for this land seismic survey, for example, and you cannot determine the depth of this event clearly. What we prefer is to record the seismic data very dense using dense receiver. So for example, if receiver interval is 5 meters, you get very clear picture about dipping event of the ground roll or direct arrival. Compared to this figure, people will choose the right figure because you can easily handle the noise or noise attenuation in the data. So another illustration is for sparse acquisition. Image is like this, but if you have dense receiver, you can get the image like this. It's clearly see the benefit of having high spatial sampling rate, so or short receiver intervals. So that the great benefit of fiber optic distributed sensors, because they can have high spatial resolution. Before the first paper published, I refer to some paper by Bakulin in 2020. They used fiber optic DAS as the surface seismic receivers, but that for land seismic surveys. At that time, there was no case study of using seabed DAS for marine subsurface exploration. So that came to the first paper. And so the first goal of this PhD thesis is to validate seabed DAS application to marine subsurface seismic exploration. So, and use term that DAS for subsurface monitoring as the title of the thesis. So the final goal, and I hope we can see in the near future, is to use fiber optic, integrate the fiber optic sensors in the subsurface monitoring. This illustration shows how it's going to be look like in the marine and seabed terrain. You deploy fiber optic cable, and you can connect that to interrogator to sense the strain data in the sea floor. So that, for example, in the future. So now next to introduce the second part of the thesis is 4D seismic for subsurface monitoring. I will start with the definition. The 4D seismic is a tool for monitoring the changes in subsurface properties. It relies on the time-lapse changes in seismic amplitude, travel time, or both. So this figure show example of how the 4D seismic image look like. We acquire the baseline data and process and get the image on the left, and year after year you repeat the survey and get the different characteristic of the image. And you can see that for this example from Sleipner, they inject CO2 gas to the subsurface, and you can see how impact of the gas when it's stored underground on the amplitude and travel time. So to illustrate clearly, there are two techniques for the seismic analysis. The first one is to determine the amplitude changes of the seismic reflection. And another one is to characterize the time shift of the seismic events. This time shift is normally proportional to the change in the plate thickness above. So there are two methods. Normally people think about the analysis of amplitude changes, but in this thesis I focus on the time shift analysis because I see some opportunity that we can improve the method, and because travel time normally is more robust than amplitude analysis in some sense. So time shift due to the changes in the velocity thickness. This is a simple diagram for baseline model, and I assume that this layer is homogeneous media, so it can easy to understand. So we shoot the seismic and ray path is straight line and reflected back to the receiver here. And after a while, we acquire the monitor model. Here you see that the thickness was changed and velocity will change because of some subsurface activity, for example, oil production or injecting the CO2 gas in the subsurface. It's easy to derive this relation between the travel time change and the thickness change and velocity change using this equation. And if it is the zero offset data where the source and receiver stay in the same location, x is 0. So we derive this formula, which exactly the same as what published by Martin Lander in 2004, where the travel time change can be computed from the thickness change and negative of the velocity change. So for this seismic time shift, the time shift of an event is the difference between its true wave travel time measured from the baseline and monitor data. So, and we can roughly give from this statement, we can roughly give the equation, approximate the monitor data written by the time shifted version of the baseline data like this one. And the time shift here is a function of time. So to study the interval rock properties, we need to convert time shift into time strains, because the time shift actually, by definition, is the cumulative travel time different from the surface down to the target. But what we need to study the interval rock properties. So that's why we need to convert time shifts into time strains. To do that, we do the time derivative of the time shift function, and then we get the time strain. So the time strain is the change in the travel time per the unit of the original travel time. So that for the travel time within the rock thickness. So that the idea is to compute the time strain for every homogeneous layer. If we have the multi-layer models like this, we try to determine the travel time strain within each thin homogeneous layer. So the effect of subsurface changes on time strain is that for the normal instance, we have still have this formula relate between the time strain and the thickness strain and the velocity strain like this. If the thickness of the layer increases, that means the positive time strain. But if the velocity increases, velocity within the thin layer increases, that means the travel time strain is decreases. So it's like this the interpretation of this equation. So final goal is that we measure the time strain from the data, from the seismic data, and we try to determine these two physical parameter, which is thickness strain and velocity strain, to describe the changes in the subsurface of the Earth. Common practice in 4D seismic time shift interpretation is first assume that we work on isotopic media, not anisotropy. And the second one is try to neglect displacement change. That means we assume that the thickness change or thickness strain is very small. And then we can link directly between the time strain and the velocity strain. But that's not really the case. So to be realistic, people assume a linear relation of thickness and velocity strain by introduce the R factor divided by the negative ratio between the velocity strain and the thickness strain, and assume that it is the constant for each rock type or rock layer. And that equation can be simplified into this form, that the time strain is proportional to the thickness strain. But in reality, this assumption is not always true, because there are many publications state that R factor actually depends on the rock lithology and the stress condition. So that means introducing R factor to this problem does not simplify the our problem, because you still need to determine R, you need to determine thickness strain. You need two parameters to determine from the same data. So it not simplify the problem. So the objective of the second part of the thesis is to go beyond these simplification and develop a new travel time base for the seismic method for subsurface monitoring. So that come to the title of the second part is for the seismic time strain inversion for subsurface monitoring. Structure of the thesis is listed here. This is a collection of 4 research papers, and this is already available in NTNU Open. You can download it and online if you don't get the hard copy today. It comprises 5 chapters followed by research paper. The first chapter is about introduction. Second is background. Third, contribution, followed by discussion and conclusion, and 4 papers. 3 papers are talking about DAS application in seabed fiber-optic cable using 3 different sources. The first one is using impulsive seismic sources. The second one is using whale vocalisations. And the third one using shear-wave resonances. That 3 applications aim to produce the subsurface image of the Earth. The last paper is about 4D seismic time strain inversion. Now we move to the first half, the application of DAS. So this is a collection of 3 papers about DAS. The first one in 2021, I published in Geophysics talking about DAS application for subsurface imaging using impulsive source. The second one, I co-author with Leah Beaufort, taking a part of doing some seismic imaging or seismic data recording using DAS for well vocalization. And this last one, there are many things about that, but I focus on the shear-wave resonance and use it as the subsurface exploration tool. How DAS works? I borrow this one from CGF, so it's quite nice illustration, and I hope you will understand about that. So distributed acoustic sensing work with light pulses in fiber optic cable. The first thing is we have interrogator where we inject the light pulse, optical light pulse into the fiber, and they will receive the signal backscatter back from the fiber. The light pulse are injected into the fiber cable at regular interval. And then acoustic sources such as waves, earthquake, ships, or air guns, impulsive sources that can oscillate or vibrate, shaking this fiber part. And then this oscillating pressure or some kind of oscillation will change the shape of the fiber, stretch or squeeze, something like that. And this one will change the position of the inhomogeneities in the fiber and the way they scatter the light back to interrogator. So in simple terms, they will change the optical phase, optical travel time of the light for each location in the fiber. And variations in the backscatter light due to this kind of stress and squeeze of the fiber can be tracked at the interrogator to tell us about the acoustic pressure field at each point along the fiber. I focus on seabed DAS application. So in paper 3, I mostly talk about mechanisms of ocean bottom vibrations. So we deploy the cable on the seabed, and we can sense a lot of signal. For example, the first category is the loading pressure responses. So this is the dynamic loading pressure change under overlying motions of the ocean. For example, if you have ocean surface gravity waves, that means the weight of the water column or the dynamic loading pressure change at the sea floor will change due to the motion of that ocean surface gravity waves. Another type of the responses is seismoacoustic response. So here, seismoacoustic wave propagation from various sources, such as earthquakes, well vocalizations, marine traffic noise, ship traffic, can be sensed by the DAS array. And I include the normal modes of P wave and shear wave resonance in near surface low velocity layer into this category also. The first application for seismic exploration is I show you in the first paper published in 2021, talking about the seabed DAS application from the impulsive seismic source. Here, the seismic source I use here is high frequency. The dominant frequency is about 600 Hertz. So, and the left panel here show the recording sorted into the common dust channel gather. So you see that we can clearly measure or record the direct arrival event and see some kind of reflection event. That means we can determine something about the subsurface below the seafloor. And in that paper, I process the data and show on the rightmost panel, this is the sample image from the seabed dust data compared to the image from the tow streamer, just one single channel hydrophone on the middle panel. We see clearly that dust image can give you a structure of the seafloor and also some kind of structure in the subsurface. The line shown here is about the determining or calculating the signal to noise ratio, but is that the figure from the paper. So that paper talk about sensing the broadside P wave at high frequency. Normally, people will think that dust will only sense the P wave propagation that propagate in parallel to the fiber optic cable, but and try to ignore their interaction with the broadside P wave, where P wave propagating perpendicular to the cable. So I introduced some optical phase change equation here that determined by the dust. So this is the optical phase change can be computed in terms of some factor and multiplied by the travel strain, optical strain, something like that. And for the fiber of a uniform isotopic material, this optical strain can be written into this complicated form. But I would like to note that this formula indicates that both strain, longitudinal strain of the fiber and the transverse strain of the fiber have some impact on this optical strain. So that means if the wave shaking induce the vibration in the fiber, it both wave propagation in parallel and perpendicular direction of the fiber should have impact in the dust data. So here I simplify this one into combine these two terms into this, and alpha is the ratio between the transverse strain of the fiber and of the outer cable, the cladding, I mean. So we can have this. So you can see that if I plot the amplitude relation with the glazing angle of the wave, you can see that at where the wave propagating perpendicular to the fiber, amplitude is quite dim. And if the alpha is equal to 1, you can still see negative amplitude here. It's not totally depend on the cosine square function. Another amplitude directivity is about the because of dust is the array measurement. So you will form the amplitude directivity for two arrays. So it comes to this term and is plotted here. And if we combine these two terms about the array measurement effect and the directivity of the dust, we come to this amplitude pattern where you can see that at low frequency of the seismic wave, you can clearly see the P wave at the low angle, but at the perpendicular angle or broadside P wave here, you may observe negative amplitude or reverse polarity from the high angle. But at very high frequency, for example, 600 Hertz in my paper, it's difficult to determine the amplitude at high angle or far offset, but you see negative amplitude at the apex of the short record. So that's the reason why we can sense the broadside P wave at high frequency. The next case is the paper 2, talk about how to use DAS data of the blue whale vocalizations. So here we can see that there are several whale calls in this series. And if we analyze spectrogram, you can see that each whale call have some characteristic in terms of changing the frequency with time. So this is make I refer to the land vibro-size, where so it's like blue whale can give the signal similar to vibro-size in land seismic survey. So this whale vocalization is quite can be called as a marine vibrator. And we pick up one of this called downsweep signal wave trend and try to process or correlate it similar way to what we do in land seismic acquisition by land vibro-size. And we got this kind of seismic profile. For this seismic profile is from one individual whale vocalization. So one downsweep here can deliver a correlated seismic profile like this, and at this location. And another location is on the right-hand side. So from this, you can see that we clearly see direct arrival of the event. We see water layer multiple of the direct arrival. We see some kind of information about subsurface in terms of reflection, whether it's about P wave or shear wave reflection, converted wave or whatever. We have information of the subsurface, especially in here. You see this kind of event. So that means if we can develop further to use whale vocalization for subsurface exploration. That is possible by this kind of study, that we get some information about subsurface from the whale vocalization. Another example about shear wave resonance. People already know already that we have effect from earthquake on DAS recording, that we can measure earthquake signal, P or S wave. And this is the frequency spectrum versus distance of the cable, showing spectra of the background without significant earthquake. We clearly see some strong amplitude here around 1 Hertz to 3 Hertz, something like that. This in Svalbard area, we refer to shear wave resonance in the low velocity layer. But if we measure in the same location of the cable with significant earthquake, when earthquake arrive, we see that they boost a lot of resonance at higher orders. So it's clearly. So in paper 3, we discussed some opportunity of using this kind of frequency, resonant frequency to determine the thickness of the subsurface layer, low velocity layer here. And currently we move forward, and based on that idea, we try to develop more method, try to pick the frequency at the first order resonant frequency and the second order resonant frequency, and then use that information to compute and build the shear wave velocity model in the low velocity layer or near surface velocity layer here as shown. So this paper not included in the thesis, but is already submitted to geophysics. That shows you the opportunity of using seabed data for subsurface exploration and monitoring using different kind of seismic sources. And that I will move to be on time, move to the next part is for the seismic time strain inversion. So the angle dependent time strains is known to most of people. And now I extend this idea and try to use proposed method to compute some subsurface change parameter from the time strain. So for anisotropic homogeneous media, we focus on homogeneous media. The two-way travel time of virtually reflected ray path is derived by this simple equation based on Pythagorean theorem. V here, big V, represent group velocity, and big theta is incident group angle. So the post-migration two-way travel time thickness is derived by this equation. Again, is based on the definition of migration and Pythagorean theorem. And then we can derive that if we have common migration velocity applied to both baseline and monitor data for migration, we can derive that this angle-dependent post-migration time strain equation, which is exactly the same equation shown in Adunbach in 2020. You have introduced this term, angle-dependent term, in this formula compared to the normal incident or zero offset time strain. I do further to approximate it in elliptical VTI media. For VTI media, we know that from Leon Thompson, they proposed this parameter for VTI media or vertical transverse isotropic media, where small v here is the vertical phase velocity and introduce epsilon and delta into equation. For elliptical VTI media, we assume epsilon equals delta, and then we can simplify and derive approximate group velocity in term as a function of phase velocity in this form. Hence, the post-migration time strain for elliptical VTI media in the previous page can be factorized into this two terms. So in the first term is vertical velocity strain, and the second term is epsilon change, the change in anisotropy. The thing is complicated because you have this term that is complicated term between angle and the epsilon value. So we need to further simplify, and I assume that we work for small anisotropic value, so we can simplify the equation into this form. And I still need to develop more method to stabilize this approximation. But given this approximation equation, we see that we can form the convex least squares optimization problem on trade by trade basis. So our observed data is the time strain measured from the post-migration stack for each angle. And this is our predicted formula, this model. So we form the cost function into this format where D is our observed data, which is the time strain. And this is the formula. It is the model data using this formula. You have X, Y, Z represent the 3 parameters that we need to determine, which is the thickness strain, vertical phase velocity strain, and isotopic change term. And then I also introduced some constraint boundary condition. For example, the first one tell you that the thickness strain need to have the same sign of the value as the time strain. The second condition is say that the velocity strain need to have opposite sign of the time strain, something like that. That the meaningful for the geological and makes sense for geological assumption. So this example, I show 3 cases. First, I show results from true time strain for the 1D model. This is a synthetic model. I first create the model in the D here as a dashed line, where there is some overburden here, where the blue line is the thickness strain is positive in the overburden, and velocity strain is decreased, so give negative velocity strain here. But in the reservoir, you will normally have, in producing field, you normally have a collapse of the thickness. So thickness strain is negative, but since the rock layer is collapsed, you increase the velocity or increase density of the layer. So velocity strain is positive here. So from that true model, I have model the time strain at the 0 angle, 5 degree, 15 and 25 and 35 as a near mid far and outer far angle stack, something like that. And I put this panel C here into our optimization problem and compute the solid 3 parameter of this in solid line to predict the thickness strain, velocity strain, and epsilon change. It's quite matched with the true. But in reality, we need to measure the time strain from the seismic trace. So I do elastic modeling to that model and get this trace and do some migration and then create angle stacks and measure it using standard correlation-based method to measure time shift and then convert to time strain and then put into the inversion program. Then compared result with the true model. It's quite impressive at the beginning, where you can predict correctly the trend of the change in thickness, velocity, and epsilon value. Move to 2D case. The top one is the time strain from the true model, and this is the measured time strain from the seismic data by elastic modeling. You will see that there is some artifact here that's not the same as the true model. That come to some artifact or error in the calculation. This slide show the results of our inversion compared to the true model here on the top. This is results of inversion, thickness strain here, velocity strain here, epsilon change here. You see that the trend is okay at the reservoir and the overburden, but maybe you still find some artifact or some error here, and especially the mismatch here. I need to figure out more in the near future about how to stabilize this optimization. I may skip the third case, but this in the thesis about the field study, which I think is agree with the well data. And for the seismic time strain inversion, can estimate the subsurface change in the thickness, and I developed the technique called for the seismic time strain inversion, but more research still required to avoid artifacts and stabilize the method. Conclusion, this is already have two parts. I already shown. First part is fiber optic DAS application. And second part, I developed the technique called 4D seismic time strain inversion. The outlook is for this research is I think we will see and more fiber optic DAS application, especially for seabed cable, and more case studies of 4D seismic time strain inversion should be expected in addition to amplitude-based interpretation. And I acknowledge all supporters, GAMES project and CGF, and thank Martin Landro, supervisor, and all data collector. Thank you.